Welcome to the lecture series of Switching Theory and Logic Design subject. In this class, we are going to discuss the design of 4-bit synchronous event counter. Otherwise, you can call this one as event counter. So, almost all the different types of counters we can implement by using synchronous counter, right? Coming to here, the synchronous counter design. So, before going to the design, let us remember one thing. Here, the synchronous counter design has totally 4 steps. The first step is state diagram. Second step is state table. Third step is reduction of state table outputs. And fourth function is designing the logic diagram by using the minimized expressions which you got from the step 3. So step 1, is the draw the state diagram. Draw the state diagram is the first step. Second step, draw the state table. What is the present state, what is the next state, and based on that, what are the inputs here we have. Those inputs you have to write down with using some Boolean function. That is the second step. Third step, you have to reduce these functions or the inputs behavior which you obtained from the truth table. So now you will get the reduced form of the input functions. Now for these input functions, you have to draw the logic diagram. That is the fourth step. Now here, the synchronous event counter. Event counter means here we have to count 0, 2, 4, 8 like that. So, for example, I am taking 4-bit event counter. So, the counts for the 4-bit event counter is 0, 2, 4, 6, 8, 10, 12, 14. After that, again 0, 2, 4, 6. Right? If 0 is the present state, the next state is 2. If the 2 is the present state, next state is 4. If the 4 is the present state, next state is the 6. If the present state is 10, next state is 12. If the present state is 8, next state is the 10. If the present state is 12, next state is 14. If the present state is 14, then next state is the 0. Right? Here you have to construct the synchronous counter by using this methodology. Here this counter has to perform only even counting. Okay, there is no necessity of the odd counting. So it should count even numbers only 0, 2, 4, 6, 8, 10, 12, 14 like that only. Okay, based on this, first you have to draw the state diagram. That is our first step. Let us see the state diagram for this step. Okay, so this is the state diagram. The first step is 4 zeros, that is 0. If the 0 is the even count, next count is 2. This is the 2, 0, 0, 1, 0. If 2 is the present count, next count is 0, 1, 0, 0. That is a 4 is the next count. If 4 is the present count, next 6. After 6, 8, 8 after 10, 10 after 12, 12 after 14, 14 after 0. So that's again the count is going to in the cyclic mode. That is, it is in the ring fashion. Okay. This is the state diagram. This is the state diagram. So this is the present state, this is the next state. This is the present state, this is the next state. Now, this state diagram you have to form as a table, right? So this is the state table. This is the state table. Okay, see here, right? This is the state table. So in the state table, see here, Q3, Q2, Q1, Q0. These are the present state outputs. Up to here, these are the present state outputs. These are the present state outputs. Next, these 4 are the next state outputs. These are the next state outputs. And coming to here, these are the inputs. These are the inputs. Okay, these are the here we have the diagram like this. So first state is Q3, Q2, Q3, Q2, Q1, Q0, 4 outputs. Next state Q3, Q2, Q1, Q0 outputs and inputs. First here, present state. The present state may be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15. Whatever it may be the value here we have. If it is 0, if the present state is 0, next state is 2. So see here, if the present state is 0, I have mentioned here 4 zeros. The next state is 00, 10. Next state is 00, 10. If the present state is 4 zeros, next state is 00, 10. Right. If the present state is 1, here if the present state is 1, there is no next state. Why? Because Here we are not considering the 1, 1, 3, 5, 7, 9, 11, 13, 15. These values we are not mentioning. If the present state is 1, I am not writing anything. I am using the into symbols, that is don't care symbols I am writing here. Next, in the same way for 2, if your present state is 2, next state is 4. If the present state is 3, nothing, no next state. If present state is 4, next state is 6. If present state is 5, there is no next state. If the present state is 6, then there is the next state is 8. So for the even states, you have to represent the next state. For the odd states, that is 1, 3, 5, 7, 9, 11, 13, 15, for these states, there is no next state. I am represented with into marks. Right. Based on this, now here you have to write down the T3, T2, T1, T0 inputs. That is, this is the excitation table. So present state, next state, and coming to the inputs. So coming to here the inputs. So present state is 0, next state is also 0. Now the T input is equal to 0. Why? Because there is no change in the output. So for that reason, the T is equal to 0. If any change there in the present state to next state, then you have to write T is equal to 1. So here it is 0, 0. When it is 0, 0, the T input is equal to 0. If it is 0, 1, then you have to write down the 1. Like that, you have to write the T3, T2, T1, T0 inputs. So after writing that, you have to now form the equations. So first you have to write down the function for T3. T3, whenever it is going to on that combinations, you have to represent. T3 is equal to 1 when the input is equal to 6 and when the input is equal to 14. In this two combinations only, the T3 is equal to 1. That is, T3 is equal to sigma small m of 6, 14. Next, T2 is equal to, next write down the function. So it is 2, next it is 6, 2, 6, 10, 14. 2, 6, 10, 14. This is T2. Like that you have to write T1 and T0. Right? I have written in the next slide. See here. So these are the functions. So T3 is equal to 6, 14. That I have written here. Next to T2 is equal to 2, 6, 10, 14. I have written here. T1 is equal to. So see here. T1 is equal to. What is a function? So T1 is equal to. You see here. 1. Almost all here there is no 0. Either 1 is there or don't care symbol is there. That is almost all the outputs are 1. Okay, for the even operations, for 0, 1, 3, 5, these are the combinations for M0, M1, M0, M2, M4, M6, M8, M10, M12, M14. For all this combination 1 and remaining combinations, we have represented don't get combination. And coming to the T0. For M0, that is equal to 0. Here all zeros are there. No 1 is available. No 1 is available. So let us see here. I have drawn T1 is equal to 1. Why? Because here some of the don't get terms are available and some of the 1 terms are available. Total, we have to make a 16 group and final output is equal to 1. And here T0 also see here for the T0. For T0, here I have represented only don't get combinations, but I don't have any ones in this. So there is no necessity of making the groups. If there is no possibility to make the group, then the output function is equal to 0. If all the elements are covered in the K-map, then the output is equal to 1. So in this way, you have to find the T3, T2, T1, T0. So T3 input Q2, Q1, T2 is equal to Q1, T1 is equal to 1 and T0 is equal to 0. Right. Now see here the 4-bit synchronous counter logic diagram. So T3 is equal to Q2, Q1. What I have mentioned, T3 is equal to Q2, Q1. That Q2, Q1 I have mentioned. So T3 input is equal to, I have drawn an AND gate. For this AND gate, the inputs are Q2 and Q1. These outputs I have connected to the AND gate and the AND gate is connected to the T3. Next, T2. T2 is equal to Q1. T2 is equal to Q1. The Q1 output is connected to here. And T1 is equal to 1 and T0 is equal to 0. So this is the connection and this is a finalized simplified diagram, logic diagram for the 2-bit synchronous event counter. Okay, let us take this one. Okay, thank you.